Hey everyone, and welcome to The Explainer. I am so thrilled you're here today because we've got a seriously fascinating subject lined up for you. We are going to take an intense, microscopic dive into ASIL B functional safety for electric vehicle powertrains. Specifically, we're zooming in on the beating heart of a hybrid dual-motor power conversion system, or PCS, and unpacking one of its most critical inverter and power stage faults. We're talking about DC link capacitor aging and degradation. We're going to see exactly how these systems are genetically engineered from the ground up to survive extreme electrical stress, step by step.
But before we get into all those microscopic details, just think about this number for a second. 60 milliseconds. Literally the blink of an eye. In a high-performance dual-motor PCS system, 60 milliseconds is the exact high-stakes window the vehicle has to detect a critical failure and execute a safety fallback. If it misses that window, you're looking at a catastrophic thermal runaway. If a high-voltage capacitor starts to fail, the system doesn't have seconds to react. It has fractions of a second. Literally, everything we are discussing today is engineered to beat that 60-millisecond clock.
Okay, let's dive right into this. Here is our roadmap, which is going to take us systematically from the physics of a failure all the way to high-stress validation. We've got 5 key phases. First, fault root cause analysis. Second, software and hardware co-diagnostics. Third, DFME key design prevention. Fourth, PFME key process controls. And finally, DVPNR validation.
Starting off with Section 1, Fault Root Cause Analysis, or what we're calling the anatomy of degradation. To really understand how to protect a system, we first need to meet the villains of our story. The degradation of a DC link capacitor doesn't just happen in one single way. It's an incredibly complex, multi-dimensional attack. First up, we've got extreme heat and electrical stress, causing what's known as self-healing decay. Second, there's carrier desynchronization, where microscopic timing errors create these huge ripple overlaps. Third, system imbalance can actually inject massive low-frequency second harmonic ripples. And fourth, something as incredibly basic as a loose bolt can cause preload loss, which leads to a massive spike in contact impedance and localized heat. Let's look a little closer at how these actually stack up to destroy the capacitor.
Let's start with that self-healing mechanism. Inside these capacitors, you have these ultra-thin layers of polypropylene film. When they're exposed to extreme temperatures, we're talking from -40 all the way to over 105 degrees Celsius, alongside high-frequency ripple currents, the film undergoes microscopic electrical breakdowns. But amazingly, it actually heals itself. The intense heat at the puncture site vaporizes the surrounding metallized layer, completely isolating the short circuit. It saves the system for the moment. But here is the catch. Every single time it does this, it permanently destroys a tiny fraction of the electrode's surface area. Over time, this sacrifices total capacity and drastically spikes the equivalent series resistance, or ESR, and because of the underlying physics of voltage ripple, this drop in capacity creates a geometric explosion of voltage ripple, severely stressing the power modules over time.
And this brilliantly illustrates our second major threat. In a hybrid dual-motor system, both motors share the exact same DC bus. So to keep the electrical noise down, engineers offset the switching signals by exactly 180 degrees. This creates destructive interference, which effectively cancels out the high-frequency ripple. It's a great trick, but what happens if the microprocessor's internal clock slips? Even a slight phase shift causes those ripples to perfectly align. This is constructive interference, and it is terrible news. It creates an absolute tsunami effect in the electrical lines, instantly doubling the ripple amplitude and creating massive heat loss right inside the dielectric material of the capacitor. Moving right along to Section 2, Software and Hardware Co-Diagnostics. This is basically the vehicle's immune system. So the physical threats we just talked about are severe. How does the vehicle actually fight back? Well, this is the data's journey from a high-voltage threat detection down to the safety of the microcontroller. First, hardware isolation uses precision resistors to safely step down that massive 400 or 800-volt DC line to a tiny, measurable window between -1 and +1 volt. Next, a 10 MHz delta sigma modulator converts this into a high-frequency bit stream, safely isolated from the dangerous high voltage. Then the microcontroller uses a 500 Hz digital high-pass filter to strip away the noise and extract the pure ripple voltage. And finally, a recursive least squares, or RLS algorithm, continuously tracks the capacitor's health, dynamically estimating its real-time capacity and resistance. When that algorithm actually detects a problem, it relies on some incredibly complex fallback logic to save the day. If the anomaly is mild, let's say a capacity drop of around 5 to 10%, the software intelligently adapts. It shifts the switching frequency up to 12 kHz to reduce the ripple charge per cycle and drops the motor torque down to 30%. This is essentially your limp home mode. But if it's severe, where the ripple spikes over 10% for just 20 milliseconds, the system takes dramatic action. At high speeds, it triggers a stepwise active short circuit, which is a brilliant two-stage maneuver to safely dump the energy and clamp the voltage under 720 volts. At low speeds, it triggers active freewheeling. And remember, all of this complex decision-making and execution happens within that critical 60 millisecond window.
All right, Section 3, DFMEA, Key Design Prevention. Think of this as genetic engineering for the hardware.
We've seen how the system reacts to a failure, but how do we prevent the failure from occurring in the first place? Well, engineers lay down some absolute mandates during the design phase. They start by specifying low ESR film capacitors with a massive 30% capacity margin and a ripple tolerance that's 1.3 times the extreme limit. Then there's the bus bar design. By using laminated bus bars squeezed down to less than 0.5 millimeter, they compress stray inductance down below an incredible 15 nanohenries. This literally starves the voltage spikes of their destructive energy. They also mathematically mandate the 180-degree carrier phase shift algorithm we talked about earlier, which cuts the total RMS ripple by over 40%. And finally, they layer in adaptive notch filters to actively suppress those dangerous second harmonic disturbances.
Which brings us to Section 4, PFMEA, Key Process Controls. This is where we nurture that robustness right on the manufacturing floor.
Because let's face it, even the most brilliant design on paper will fail violently in the real world if it isn't assembled perfectly. The oversight on the factory floor is intense. To prevent those tiny microimpedances that cause localized thermal runaway, they use 100% automated 3D X-rays or ultrasound scans on every single laser weld. For the bolts holding the high-voltage bus bars, humans with air tools are completely banned. They use servo-tightening drivers with strict torque angle curves on specific phosphate-coated bolts to guarantee the contact resistance never, ever exceeds 5 milliohms. Finally, an automated end-of-line test injects precise voltages at both room temperature and high heat to flawlessly calibrate the sensors and lock those values directly into the system's memory.
Now, what's really interesting about this slide is this super strict tolerance, less than or equal to 5%. This is the absolute maximum voiding rate tolerated in the laser welding of the capacitor pins. Furthermore, any single void cannot exceed 1%. If an automated 3D X-ray detects a 5.1% void, the entire production line literally physically locks down, isolating the part. It really proves just how uncompromising ASIL B quality control has to be. Finally, we've reached Section 5, DVPNR validation, the ultimate stress test. Before the system is ever trusted on a public road, it has to survive an absolute gauntlet. So the crucial point here is that passing isn't subjective. It is heavily quantified. Just look at these 3 trials. First, they literally bake the PCS at 105 degrees Celsius while pumping 120 amps of ripple current through it for 1,000 hours. The internal temperature rise cannot exceed 15 Kelvin, and total capacity can't drop more than 3%. Second, they hit it with rapid thermal shocks and random 3-axis vibrations. The exact acceptance criteria? Resistance cannot increase by more than 1.2 milliohms, and there can't be a single physical disconnect lasting even 1 single microsecond. Third, they hook it up to a high-fidelity simulator running a virtual motor at 12,000 RPM and artificially inject a massive 50% capacitor failure. The system has to recognize the fault and clamp the voltage safely under 720 volts, all in under 60 milliseconds. We've traced the entire journey today, from the microscopic vaporization of film deep inside the capacitor all the way to the extreme gauntlet of 1,000-hour stress tests. It highlights a massive engineering reality. Hope is definitely not a strategy when it comes to high-voltage electric vehicles. I want to leave you with a provocative thought to chew on. Based on the incredibly multi-layered microscopic defense strategy you just learned today, ask yourself, is your PCS architecture truly engineered to survive the ripple? Thank you so much for joining me today on The Explainer. See you next time.